We have one last chapter to cover, and then you're all set and ready to go for exam 2. Good news. This is a short chapter. Also, if you've been doing the calculations from previous chapters, I think this chapter should go really well, but we'll get to it. So a couple of reminders: homework, chapter 7, chapter 8, those are out there and due on Thursday. I have posted a lot of practice problems now, so if you don't want to attempt the homework and lose points, if you just want more additional practice, they're categorized so you can take a look. Maybe you want practice naming, go take a look at the naming practice. As always, see me during office hours if you want to go over any of these examples or have questions. You do have quiz 3 on Tuesday, so that's going to be on this April 7th. Please note the quiz, you have 1 hour to take this. So once you open up quiz, you have 1 hour, and it is only available on certain times from April 7th to 9th. So you can take a look on Canvas, see when that's posted. Basically, when I finish office hours on Tuesday to when I start on Thursday, that's when the quiz is available. And then Thursday, the only thing that you have is exam 2. You'll be given 2 hours for that. Same, you'll be given a range. Once you open it up, then you have a certain time to complete it. So make sure you're ready to go. That's the plan for the week. Chapter 8, quiz 3, and exam 2. As I mentioned, this is just some small topics, very short topics to cover. But if you haven't been doing the calculations, it could be a lot, a big order. So we'll get started and take a look. We've been talking about this, viewing things on the molecular level or the particle level. Okay, that's the goal of this assignment, is thinking about things like this. Now we're going to add the calculations to this. So the reaction to burn your gas to produce CO2, to produce water, how much is being produced, and things like that. These are the questions of this. It's all about quantities, so it's for sure heavy in calculations. So you've probably seen CO2 production in mainstream news, lots of places. It comes from this equation right here. If you produce carbon dioxide, and this is one component of gasoline, octane, well, how much are we producing? Okay, and actually you could look right now with the less driving and the less use of octane, then of course less CO2 is being produced. Okay, so these are the calculations we're going to look at. It starts from having a balanced chemical equation, and then it goes to the roadmap that you remember. Oh yes, our wonderful roadmap, grams, moles, particles. But now we're just saying we can change it into other things. We did this already with formulas, but now we're doing this with chemical equations. Okay, and if we do that, we change from one substance to another. This is called stoichiometry, the area of stoichiometry. So let's say you have grams of octane. You know how to convert that to moles of octane. That's the molar mass. And then if we want moles of CO2, well, that's this mole-mole conversion, and that would be the mole ratio of octane, 2 moles CH18 over what you're going to, 16 moles CO2. So really we're not adding anything new on this slide. You've done mole ratios, you've done grams, moles, particles, you've converted that to grams, moles, particles of something else. So now we're just looking at it in light of a balanced chemical equation. So your author does an interesting thing. Well, takes it to something practical. If there's a recipe for 5 pancakes, there is certain ingredients with certain amounts. Okay, well, you take a look. This is what it makes. That's a chemical reaction, right? This plus this plus this equals 5 of these. So it's the same kind of relationships in chemical equations, and that's what we're going to be looking at. Well, wait a minute. What if you had a dozen eggs and everything else to eat, enough ingredients? How many pancakes could you make? So you just look at the ratio. Everything else is there. You know for every 2 eggs, you can get 5 pancakes. If it's a dozen eggs, so we're getting 12 of these. Okay, so let's say 12 eggs. Set up our ratio, 2 eggs, 5 pancakes. It's getting sloppy, and I think I'm going to run into the answer too. You can see, maybe you can't see, that can give you 30. So that would be 12 eggs times 5 pancakes over 2 eggs. That gives you a total of 30 pancakes. That's how much you can make if you had a dozen eggs and everything else that you needed. So these are kind of questions. Maybe it's not as exciting, a little more boring. Hydrogen, nitrogen, ammonia. You got to have a balanced recipe or a balanced chemical equation. That's 1, that's 2. So we can do calculations for these. Okay, if you had this much hydrogen, how much ammonia can you get? If you had this much nitrogen, how much ammonia? What if you had this much nitrogen, how much hydrogen will it react with? So all of these are questions that could be asked that go in this chapter. So let's take a look. Starts with a balanced chemical equation. And like I just showed, it could be asking about reactants. It could be reactants converting to products. It could be product converting to reactants. And remember, when we're balancing, that balancing is all about the moles. Okay, so if you're given grams, if you're given volume, if you're giving something else other than moles, you have to get it into moles, because that's what a balanced chemical equation is in moles. So if you have a balanced chemical equation, you know moles of one thing, you can know the moles of anything else. That's the beauty of a balanced chemical equation. And as I mentioned, this is called stoichiometry. So lots of calculations, grams, moles, particles, and then moles of one thing go into moles of something else in a chemical equation. So let's take a look. Example. Here, this is propane and oxygen, gives us carbon dioxide and water. And we got lots of relationships. 1 mole of propane reacts with 5 moles of oxygen. 1 mole of propane produces 3 moles of carbon dioxide, or 5 moles of oxygen leads to 4 moles of water. So we have lots of relationships. That gives us our ratios. So no matter what is being asked, you can look at the balanced chemical equation and get these ratios and then do the math. So for those that are still struggling with dimensional analysis, setting up the unit, canceling the unit when you divide by it, going to another unit, this is where, we want practice on that. There's practice on the homework online. There's practice problems. You can just do dimensional analysis, but we're going to be doing a lot of that in this chapter. All right, so here's what you're going to be doing. Write a balanced chemical equation, and you've got that. Then there's 2 common calculations. Convert moles to moles of something else. Okay, mole ratio, no problem. Or grams to grams of something else. Okay, so again, our grams, moles, that's what we're talking about, roadmap. In this case, because we're talking about 2 different substances, we need to go through this balanced chemical equation roadmap with the mole ratio. Remember, we did do this grams to grams with mass percent previously, but in this case, balanced chemical equation, we're going this route. So we've got to go through moles to do this. All right, so let's take a look. You're given moles, and oxygen's right here, and octane is the other reactant, that's the excess. How many moles of water would form? So these are the things that we're looking at. So really it's water and oxygen. We got enough of this. You're not being asked about this, so it doesn't matter. Okay, so if you're in moles of oxygen, you want to set up your ratio. So moles of oxygen is what you're starting in. Then we've got to be multiplying it by moles of oxygen to cancel. So if we look here, balanced chemical equation, that's 25 moles of oxygen. Then you see where it's being asked to go. It's water. That's 18 moles of water. So what I'm trying to emphasize here is where this mole ratio comes from. Okay, so that balanced chemical equation looks a little sloppy. It's cleaned up here. 18 moles of water. Emphasize, what are your moles of? 25 moles of oxygen. So moles of oxygen cancels with moles of oxygen. This does not cancel because that's your final answer and the unit for that. 0.019 moles. Okay, so that's moles to moles. Mentioned there's two types, moles to moles or grams to grams. So you can see here how many grams of glucose, that's the C6H12O6, can be synthesized from 58.5 grams of carbon dioxide. So these are our two things. Assume that there's more than enough water, we don't need to worry about this, to react with all of them, okay? Or we're not thinking about oxygen either. So, remember, roadmap, grams, moles, moles, grams, and in this case, this is CO2, that's CO2. So remember, this is molar mass right here to get from grams to moles. And then if we're going moles of CO2, moles of glucose, we have to think about the mole ratio. That's 1 here and 6 here. So that's going to be this 1 to 6 mole ratio. So if you take a look, molar mass, remember that we look up from the periodic table, carbon's 12, oxygen 16 times 2. That gets us our 44 with some sig figs here. The 1/6, the mole ratio, comes from the balanced chemical equation right there. And then if we're going to grams of glucose, we gotta get the molar mass of glucose. So that's carbon, 6 times 12, 12 times 1, 6 times 16. That's where your 180 comes from to get your final answer in grams. So those are your two main calculations. Let's take a look at another one. Got more than enough O2 and water. We're interested in this HNO3, this nitric acid, in kilograms. And you're given kilograms of NO2. Okay, so NO2 to HNO3, look, mole ratio, 4 to 4. Oh, that can be tempting. Well, it's just, 1 to 1, no problem. Don't forget, you're in kilograms. Okay, so our pathway, kilograms, grams, moles, moles, grams, back to kilograms. This is our roadmap that we're going. And if you take a look here, metric conversion, molar mass gets us to moles. I know this doesn't change the value. 4/4 is just 1, but it changed the unit. That's the big thing here. And then we go back to grams by molar mass and go back to kilograms by metric conversion. So that's our total kilograms of nitric acid. So not everything goes perfect. What happens if you run out of something? Okay, that's not enough ingredients. So 1 cup of flour, 2 eggs, half teaspoon baking powder, 5 pancakes. Well, if you take a look, 15 pancakes from the flour. So you see here, this is 1 cup of flour, but we have 3 cups of flour. So that can give us 15 pancakes. Okay, and if you count the eggs, do the ratio, 5 to 2, that can give you 25 pancakes. And half teaspoon, and we've got 4 of those teaspoons, that can give you 40 pancakes. So what we're seeing is clearly you can't make 40, 25, and 15. So what it's saying is if you run out of flour, even though you have enough eggs to make 25 and you have enough baking powder to make 40, you cannot make more than 15 because of that. That is your limiting reactant. You run out of that, you're done. You can't do anything else until you go back and get replenished. So limiting reactants looks the same, balanced chemical equation. And then you think, what does this look at the particulate level? 2 molecules of CO react with 1 of this, 2 of these are formed. So what we're seeing is that this limiting reactant gets used up first. Okay, that's what we're talking about here. And we're thinking on the molecular level, but of course we scale up to the mole level as well. And that's what we're doing with our calculations. So, limiting reactant problems, we have more information than what we've previously been working with. Okay, that can get confusing for sure. You see right here, this is a double stoichiometry problem. So you solve this by running 2 calculations, and then you realize, just like with our pancakes, we want to circle the smallest number. Remember, the smallest number is the one that's going to be the limiting reactant. It runs out first. So let's take a look. How many moles can be formed if you begin with 0.552 moles of aluminum and 0.887 moles of chlorine? So we need all of this information. Okay, we've got aluminum, we've got chlorine, and it's saying how much can form. So you need to see how much can form from that, how much can form from this, and then we're looking for the lowest. So same calculations we've been doing. Mole to mole ratio, mole to mole ratio. You can see here it comes from the chemical equation, so that's 2 aluminum chloride. That takes care of that one. This is 3 moles of chlorine here, 2 moles of aluminum chloride. Do the math, we get 0.591, 0.552. This is a smaller number. That's the least amount of product. Okay, so that's what can actually form. That means that our aluminum is the limiting reactant. That runs out first. And you could say our chlorine is in excess. So we've got limiting and we've got excess. All right, so let's go to grams then. You can see same kind of problem, grams of one thing, grams of the other, and what's the maximum amount of ammonia? So this is what we want to know. 2 problems then, how much ammonia is formed from hydrogen, how much is formed from NO. So 2 problems. This is grams, so of course I got to put the roadmap up. Grams, moles, moles, grams. Oh yeah, double times 2, double stoichiometry. Okay, we do 1 for NO, we do 1 for hydrogen, so that's grams to moles, mole-mole ratio, grams to moles, 26 grams of ammonia. Second, you're doing 2 problems in one, right? So then this is grams to moles, moles to moles, grams to moles, and grams of ammonia. But you're not done. You have to compare. 26 is less than 41.8, so you have to know that number's smaller, which makes this the limiting reactant, which makes this the excess. So this, in theory, that's why we call this the theoretical yield, that's what you can make. You can't make this. It's impossible to make 1.8 grams of ammonia because you do not have enough NO. Okay, so that's not under consideration. This is our theoretical. That's what you can do. Well, theory, of course. What does this mean? Well, real life doesn't always go as planned. Isn't always completely theoretical. So you can't have complete conversion to products. If there was complete conversion, I mean, you've been in the lab collecting products, spilling things. You can't do 100%. You can't be perfect. That's just the nature of lab. So the reality is you have a chemical reaction and you're going for this product, and you may have side products, you may have some contamination, you may have lots of things, and you do not get perfect product. you do not get 100%. Okay, that's what is real life. So we want to evaluate that. How do we evaluate it? We have to know what the theoretical yield is, what is actually possible from the calculation. So this is theoretical. That's all about a calculation. What is possible with this setup? Then do it and collect. What's the actual yield? What is actually recovered in the lab? And then you can evaluate with the percent yield. So percent yield is actual over theoretical multiplied by 100. So now we can put all this together. You've got grams of carbon, and you've got grams of copper 1 oxide, and you've got grams of copper that are obtained. Determine the percent yield. Okay, so there's a lot going on here. So let's look at this and see first. Okay, you've got grams of this reactant right here, and you've got grams of this reactant. This should be a red flag right away. This is a double stoichiometry problem. Okay, that's grams, moles, but you've got 2 reactants. That means you've got to do it twice. And when it says 87.4 grams of copper are obtained, this should be an indication, red flag, however you want to think about it. This is called the actual. That's what was actually done. Percent yield from the slide before is going to be actual over theoretical multiplied by 100. So we need to calculate the theoretical. That's what we do up here. That's what's already been done. Grams of carbon, grams of copper 1 oxide, go the pathway, grams, moles, grams. That's how much grams of copper can form from this carbon. Grams to moles, mole to mole, and so on. This is how much copper. So clearly you can't make this. It's not possible. This is the limiting reactant. It runs out, and this would not form. This is the least amount of product. If that's the least amount of product, that's the theoretical yield. So 101.7 theoretical yield, the actual 87.4. That comes from the problem because you're not doing this in the lab and collecting, and that's your overall yield. So that's the bulk of this chapter, calculations, grams, moles, particles, but really we just did grams to moles, and then the mole ratio, and then moles to grams, or you just went to moles directly. Those are the heavy calculations. The last piece, you've already seen this in lab on campus, and that's when you had heat associated with reactions. Well, that was an exothermic or an endothermic reaction that you could have observed. And it depends on how much stuff you had, okay? So the amount, so was it really, really hot or was it really, really cold? This is the enthalpy. And we can see that the enthalpy, the heat of a reaction, the variable is called delta H. That's the enthalpy, delta H. That depends on how much you have, okay? So in my labs in particular, I really emphasize first the sign. First we want to know, is it endothermic or is it exothermic? So that's a sign. That's all we look for is sign. Endothermic, exothermic, X is negative, endo is positive. Delta H has a negative number in it, it's giving off heat. If delta H is positive, it's taking in heat. That's what we want to look at first and be able to compare it. What does this mean, taking in heat or giving off heat? Well, if you think about an energy diagram, and if it's going from a high energy to then it ends at a lower energy, it's got to be giving off heat. That's exothermic. Or if it goes from a low to a high, it's got to be taking in heat. That's endothermic. So what does all this mean for our chemical reactions? That's what we've been looking at, grams of chemical reactions, products, things like that. Well, we can have a balanced chemical equation, and now we can add this piece. Okay, so if we look here first, delta H is positive. That tells us This is an endothermic reaction. Okay, and then if we look, a balanced equation, this is called a thermochemical equation. So now you know for every 2 moles of water, it takes 572 kilojoules of heat. If you produce 2 moles, that's the same number. 1 mole, same number. So these are mole ratios. Okay, it's the same thing we've been seeing from this 2 moles of water to 2 moles of hydrogen. We're just adding this as now another piece that we can do as a ratio. So let's look at a few examples of this, because we're going to use these in calculations now. So this is strange, I know. Sometimes you'll see fractions in balancing. Here, just wanted to put this in to show you delta H is negative 57.1, and that's for every 1 mole of NO, or that's for every 1 mole of NO2. So we're just setting up a ratio, or because of that half, that strange thing of oxygen, we can say the same thing. So these are ratios that we can use in a calculation. So the last example we have here then is we've got balanced chemical equation, 1 mole of propane, and if you look right away, that's exothermic. It is giving off heat. So it says calculate the heat associated with the complete combustion of all of the propane in the tank. So our propane is here, 11.8, and that's in grams. So we're going to need to go from grams to moles, and we're looking for the heat in kilojoules. So you know this, no problem. Grams to moles, nothing new. This piece, you can see the ratio needs to be this. Moles on the bottom, kilojoules on the top. If we look, we saw that's 1 mole of propane. And that's where this comes in. So we just add the ratio in and do the math. So grams to moles, and this is the new piece that's being added. We're getting a ratio of moles to kilojoules, final answer in kilojoules. So that concludes chapter 8.